Hello, everyone. So, last time, I guess I should say, we looked at projectile motion where all the initial velocity was in the x direction. Now the initial velocity is at an angle, which means it has an x and y component. Okay, so that's what we're going to be talking about today. Now, a couple things to keep in mind. Sorry, this didn't print really well. Let me write it off to the side. We have 4 kinematic equations that we're going to be working with. Okay. And so I have them written down. So we have velocity final equals velocity initial plus acceleration multiplied by time final. Okay, so that's our first one. And then our second one, velocity final, and we're going to make all of these in the x direction, and then recognizing it could also be in the y. So velocity final equal squared will equal velocity initial and the x squared plus 2 times by acceleration times by delta x. And then we have our third equation, x final equals x initial plus velocity initial in the x multiplied by time final plus 1/2 acceleration time final squared. And then, oh, sorry about that. Then our last one is delta x is equal to 1/2 velocity final plus velocity initial, all multiplied by time final. Okay, so here are our 4 equations. Couple things to keep in mind. The top 2, they do not work, okay, or these ones only work if acceleration is not equal to 0. Okay, so if the acceleration is equal to 0, then we're unable to use these equations. Okay, but we can, and so if acceleration is not equal to 0, then this is all good. We can use all of them. If acceleration is equal to 0, then we can only use those 2. Okay, and then the other side of this, every time I've written an x, it could be replaced with a y. We'd have the same equation for the y direction. Now, if we have projectile at an angle, this is our initial velocity, right? It's at some angle, and the projectile will go up, and then it'll come back down, and eventually it'll hit the ground, right? What is the initial velocity? The initial velocity now has a vertical component, right? So if I were to zoom in on this velocity, okay, and so this is my velocity initial. It now has an x and a y component. We have velocity initial in the y as well as velocity initial in the x, and will be some degree theta above horizontal. So now, what is the acceleration in the y? The acceleration is still the acceleration due to gravity. When the object is flying through the air, the only force acting on that object is the force due to gravity. So 9.8 negative, because it's going down 1 meter per second squared. How does the velocity change in the y? So for the first part, we have a positive velocity. We have a positive velocity, but we have a negative acceleration. So do you see how in the y direction, we start with some velocity, we slow down, we slow down, we slow down, and in the y, not the x, but in the y, we're going to get to a point for the briefest of moments that we stop, and that's going to be the apex, the very top of that parabola. And then we start increasing our velocity in the negative direction because of that negative acceleration, and then we speed up as we hit the ground. Okay, so at first we slow down and come to a stop, and then we speed up in the negative direction. Okay, that's how our y velocity changes. What about the x direction? There's no forces acting in the x, and so the acceleration in the x would be 0. And so how does the velocity change? In the x direction, it doesn't. It's going to travel the same distance over the same amount of time in the x direction. Okay. So it's kind of small, but I want you to look closely on your notes. Focus on the y component. So see how we have some velocity vector, and then we have our y component of that velocity, and see how it's getting smaller and smaller and smaller and smaller. And right here in this moment, we do not have a velocity component in the y. It's all in the x, and then it starts getting bigger and bigger and bigger and bigger as we increase, as we go down towards Earth. Okay. Okay, now, how does the initial velocity affect the range for a given angle? Explain. So, something to keep in mind. We do have an optimal angle, okay? And so what we mean by this is if I'm always at 45 degrees, but I increase my initial velocity, then the object will go further and further and further. But what if I keep the same velocity? What if in every single situation it's 50 meters per second is my initial velocity, but I'm changing the angle in which that happens, okay? And so it turns out that, shorter angles, we're not going as far, and then we increase and we increase, and eventually we get to 45 degrees and we see this maximum distance obtained. And then after we increase beyond 45 degrees, the opposite occurs. We become shorter and shorter and shorter, right? Because see, if this is my big angle, it goes up and then it comes back down, and it hit a lot closer than it did when I was at the 45 degree angle. Okay? So any combination of trajectories that add up to 90 degrees will have the same range. So here's what we're looking at. This one was 75, okay, and that one was 15, and they landed in the same spot. So if you take 75 plus 15, so that would give us 90, they're going to land at the same location. So that means that I could tell you the location of one angle, and then you could tell me the other angle that would land that same distance. Okay, there's our kinematics again. Oh, all right, example number 1. Okay, let me see where we're at time-wise. All right. So let's set up this problem. A ball is launched 4.5 meters per second at a 66 degree angle above horizontal. What is the maximum height of the flight? Height and flight time of the ball. Okay, so let's draw a picture. So we have, here's our ground. We're launched at this angle. We're going to go up, and then eventually we're going to come back down, right? Okay, if I zoom in on this, and I want to see what's going on there, I have a big initial velocity, right? And it's broken up into velocity initial in the y and velocity initial in the x, and the angle is 66 degrees. And I'm going to make that starting point, that's going to be my origin. Okay, that's going to be my 0, 0. And I want to know the maximum height. So that means at the apex, right? So if this is my initial position, this is going to be my final position. Okay. We have this triangle here where we have velocity initial in the y and the x, and we know that the overall velocity was 4.5 meters per second. But with our trig skills, we can determine what the y and the x component is of that. So if I want to figure out velocity initial in the y, it is opposite from the angle. So you take the hypotenuse, that velocity initial, and I'm going to multiply it by the sine of the angle, okay? So velocity initial in the y, I'm going to take 4.5, I'm going to multiply it by the sine of 66. And so my initial velocity is 4.11. Now something I want to note here, with these problems, and you'll see this a lot in the future, we're doing a lot of calculations, and we're going to wait till the very end to round for our significant figures, okay? So I have 4.11, and I'm going to just write out what my calculator is giving me, okay? And that's going to be meters per second in the y direction. Now, velocity initial in the x is going to be that hypotenuse, velocity initial, and then it's cosine theta, because I'm adjacent to the angle. And so then when I plug that in my calculator, the 4.5 multiplied by the sine of 66, cosine. Sine of 66, I get 1.83031. Okay. All right, so we know our initial velocities. We've drawn a picture. We've established an origin. Now let's make our lists of knowns and unknowns. Okay. So in the x direction, x initial, x final, velocity initial, velocity final, acceleration, and time. And same thing in the y. Okay. And let's see how much we know right now. So initially, I'm at the origin, so I'm starting at 0. In the x direction, my final position is right there, right? I don't know how far that is, so I don't know x final. Velocity initial in the x, though, I do know. I calculated that. Okay, so that's my 1.8303 number. Okay, velocity final in the x. Well, remember, in the x direction, the acceleration is 0. So that must mean there's no change in velocity. So whatever I'm starting with, I'm ending with. So I also end with the same 1.83031. Okay, I don't know the time component. Now let's move on to the y's. Okay, y initial, I'm at the origin, right? So that's going to be 0. Y final, I'm all the way up here. I don't know what that is, but don't you think that would be the maximum height? So that's one of the things that I'm looking for there. Oh, but we'll come back to that. We're going to start here. And then y initial, velocity initial in the y, we solved for that. That's going to be 4.11095. Our velocity final in the y, well, we're right at the very top of our parabolic motion, okay? And think of it if we were just focusing on the y direction. Let's say I have this pencil, and I throw the pencil up in the air, and it reaches the very, very top of that motion, right? It's slowing down, it stops, and then it speeds up as it comes back down. So when it's at the very, very top, for the briefest of moments, the velocity in the y direction is 0. And we can make the same justification with projectile motion in 2 dimensions. As far as the y direction goes, we slow down, we slow down, we slow down, we stop, and then we speed up. So when we're at the very top of our arc here, the velocity final in the y, that's going to be 0 meters per second. Our acceleration is due to gravity. Okay, we want to know y final. Let's see, do we have a kinematic? We may have a kinematic that we could solve for this without having to have the time component. Let's check on that.